Hi, how's it going? My name is Cody Raby, and today in this video I'm going to be touching on some of the overarching concepts I learned throughout computer science. I'm going to touch on some niche parts of it, and I'm doing it all in one take, and I'm going to try to do it as quickly and efficiently as I can. First of all, I'm going to kind of be simple. Some of the stuff I'm talking about is just to get the person listening into the right headspace. This is kind of what the makeup of my degree was percent-wise. You see 20% discrete structures, 25% programming, 20% algorithms complexity, 15% systems, and then other. This is like databases, SQL, that sort of stuff. This is like SRS documents, stuff like that for object-oriented programming. Validation, like test-driven development, and then the other is just stuff that is not encompassed in these above. I'm going to let you look at this for a second. This is pretty useful information. This also comes from my university, but I tweaked it a little bit to what I think is more accurate. And then to get us in the right headspace, first of all, computer science is fundamentally connected to programming. All right. So programming is kind of like a subset of computer science. Computer science covers like everything computer related, but programming is a key part of it, right? What is a programming language? A programming language is a collection of statements and the ability to maintain state, process data, and basically perform functional instructions. A programming language is what you tell the computer to do, how you do it. You type in that programming language, and then the compiler, interpreter handles that, and the computer performs those operations. How does a programming language affect the way we solve a problem? Different problems are better in different languages. Something data processing heavy you might want to do in Python, so you can use built-in libraries that exist for that. What is an operating system? What does it do? An operating system, or OS, handles scheduling of different processes, which the processes handle threading, which I'll touch on a bit later. It also includes the file system and taking input from the keyboard or mouse, whatever external hardware you have plugged in. Even the camera handles that. Or camera. I don't know what I said. But, anyways, what is a terminal? A terminal is a command line interface to type your instructions to your OS. What is a text editor? This is a text editor. Simple as that. A text editor is simply a program that allows you to write things in textual form, and you can also use these text editors to write code that you can put through a compiler or interpreter to handle, or you can give that code to like a make file or something and run the code. What is syntax highlighting? Basically, this right here, I was using for an example earlier, but you won't see it in this video. So syntax highlighting is the difference between these colors here and how easy it is to read the code. Functions, these are functions, they're all the same color. The variables are blue, the return statements are purple. That is syntax highlighting. It makes it more readable for the programmer or person reading the code. What is an IDE? How is it different from a text editor? IDE is basically an integrated development environment. That is what it stands for. Visual Studio Code, like right here, is an example of one. I can easily debug my code if I want. I can easily run it through the terminal, through even just up here and then run the code. It also has the syntax highlighting. It has all my tools in one place. It is a convenient place to handle my code. And the next thing is, what is a comment? What type of comments should you write? Basically, a comment does not affect the actual code that is running. This program stops at y over 50, and it multiplies y by 2 recursively until it reaches blah blah blah, right? I would word this a lot better if I was doing it on the fly, but that is a comment. It does not affect the code. It is for readability, for understanding functions. It is very important in stuff like Java doc, which, if you know anything about Java, there's a lot of Java doc, especially in object-oriented programming. And then, what is a style guide? Basically, a style guide is just the rules you're going to abide by when you're writing your code. So maybe your team has a rule where after every function, you have like 3 indents, something like that, right? Maybe each variable has to be tabbed, whatever it is. And the style guides also, for different language, you can see here, oh, the X isn't working because it's not where it should be. That's pretty simple. And then, what is a difference between a syntax error and a logical error? A syntax error is simply, oh, I misspelled it, it's squiggly, I can fix it. Okay, let me fix this. Um, recursive, yeah, bam, fixed. All right, that's a syntax error. And then a logic error is this, which you'll see right here, which this probably spoils it, but you will see it anyways again. So py test.py, I'm running the code, and you can see we get this error. So the reason for this error, it says XU's recursion to, blah, 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 same line over and over again, repeated over 996 more times. This is an infinite loop. So it returns itself, calls a function, returns itself, calls a function, returns, it just goes forever and ever. That is a logical error that you would need to fix, which I had right here. Bam. I have a if block that returns just y at what it's at, if y goes over 50. So that is a logical error. The dry principle. So this is very important. This is a super important concept. It's very basic but important. You have a big piece of code. You're reusing the line y equals y plus 4. All right. For some reason, that's just being reused everywhere. You can simply make a function that is handle y or something like that. That could be the name, and it would be literally return y equals y plus 4. It would return whatever you passed it for it, and you could put this function everywhere that instance in the code is, and it would optimize it and make it a lot more efficient. It would also make it more readable, like a lot more readable. That's important for object-oriented programming. That concept is rudimentary for that. And then our next question is, what is a standard library? So basically, that is just a library that is built into these languages already. Stuff like vectors, strings, these come from standard libraries in C++, other languages as well. There are other libraries you can also import. An example would be in here, pandas. Pandas is a really big library for Python. Helps with um, data science. A lot of data science related problems are very um, easily done using pandas and some other tools. Basically, it's something that someone has already built for you to use just by importing it and using their built-in functions and other. What is a package manager in the context of a third-party library? That's something like Gradle, Makefile. It handles basically just your package management. It's as simple as it sounds. And I'm going to touch on these in a little bit. I'm going to come back to these. So, first of all, let me mention a concept called regular expressions. So, what is a regular expression? This is a sequence of symbols or characters that express a string or pattern to be searched for in a longer text. So, basically, you have a text with 100 million words, right? It's like a huge dictionary type document. If you had this on a computer, you can use regular expressions to search for very specific keywords that you want to find. Which I have a whole list of rules here, which I'm going to keep it right here for whoever wants to screenshot them. My wording might be kind of ugly, but the concept will make sense when I get to the examples. Also in this video, most stuff I go through, I will be going through by example. I learn better by example. I also think it's kind of boring to just touch on everything, just definition, definition, which is why I skipped the rest of these and I will come back to them. So the concept of regular expressions, I will show through an example down here. First of all, this one, I'm just going to touch on a couple of these as an example. You have slash, the W. W stands for, I think, word. I don't know exactly. I just know what it does. And then you have in the curly brackets 4. So this will be anything in that document that is 4 characters or longer. All right. So if I were to add 4 comma 5, anything that is 4 to 5 characters longer will be matched. This right here will match anything in a document that has either, this is regular brackets, it will match anything that has either F or C as the starting character, and then ends with AT. So fat, cat, anything that says fat or cat will be matched in this document because of the brackets here that allow that. You could also do brackets A through Z, and it will match any characters that end in A through Z at the end. That is an example of the regular brackets. Let's see. Let's do an example, alright? So right here, to search for a phone number, a string is given this 1, 2, 3, 4, 5, 6, 7, 8, 9. There's no dashes between. It's just a regular string. So to find that, all we have to do is /d, 10 characters long, and then just our global world, our global at the end, that's always there. Um, it just stands for global. It means any instances of the search for the regular expression will appear throughout the whole document, not just the first one. So basically, if I want to define the first one, all I have to do is this, in the curly brackets, 10, the length of the characters, the digits, D standing for like the number. And then if I wanted to look for the second one and the first one, then this is how I would do it. This would give me both these if I were to search. So the same thing, the digits, 3. So the first three, 1, 2, 3 characters, that's this. And then you have a dash and a question mark. Dash means the character dash needs to be there, but it's optional. So if it's there, then it'll pop up, bam. If it's not, it's fine. It'll still continue with the rest. And then same thing, 3 and then dash optional again, and then end with 4 digits length. And then the global variable again is fine. And that would give us both of these in a search for the regular expression. If we want all of these, so this is what we have to do. Digit 3, length 3, first 3. And then we have our optional brackets again that I touched on earlier. The dash or the star. So either of these can be there or none because the question mark is there. And then we go to the next digits again, 3 digits again. 1, 2, 3. Either this or there. We already touched on that. And then 3 digits again, digits again. It's optional because of the question mark, so this is still there as well. And then we do the same thing, the optional dash or star. Okay, we got that. And then the 4 digits to end it. So this would give us all 4 of these instances of a phone number throughout a document. And it doesn't have to be 1, 2, 3, 4, 5. Any phone number in this format in a text file would be found. And basically, this can also be used for stuff like um, cracking codes. Cracking codes, I guess, is a way to put it. So this example problem is given a password that is 3 digits long. So a password could be 443, something like that, just 3 digits. The numbers are 0 through 9. All numbers are allowed, and they can be reused. What would this look like in regular expression? It would look like this: 0 through 9. All numbers are optional, and length of 3. That's what it would look like, which you can see here, these rules, they're consistent. Then you have 10 options for the digit, 0 through 9, and 3 total digits. How many total combinations could there be for this password? That would be 10, the optional, like the option amount of digits, to the third power. 100 or 1,000 possible combinations is the amount of combinations for this problem. So basically, if we're given the same scenario, but you cannot reuse the numbers, what would this look like in regular expressions, and how many combinations could we get? That is right here. You can see that we start with 0 through 9 optional. The question marks exclamation point basically omits the previous one that was available, and then continues, fill it out. Get this. This looks ugly. Ignore that. Not that important. All right. Basically, for the combinations though, we have this. We have 10 times 9 times 8. We get rid of one option digit because you cannot reuse each time, and you get 720. That also connects with number theory, which we're going to touch on next. Um, right here, this is basic matching. Basically, if you have a cat and you're looking for a cat, any cases like capital, lowercase, whatever, cat slash I, bam, matching digits. We already talked about that. Slash D is for digits. D plus basically ensures that one or more digits are matched. We have a regex to match both color and color. We can put the question mark there to make the U optional, because it's the same thing with a U added, but it's not required, kind of like we were talking about. And right here we have basically where the word cat can be. If it's at the end of the sentence, at the start, so you put cat slash B, and it will match cat only if it's at the end of a word. It does not match catalog. And then for B cat, we would have only if it's at the start of a word. Um, so it would match catalog, it would not match scatter. Pretty basic concepts. That's kind of, I'm not gonna go in depth on these, but they're there. I'm gonna keep them on screen for a second, and anyone can look at them, read them. Um, Regular expressions are not overly complicated. I don't use them a lot, I will say, but they are fundamental and pretty easy to understand. There's a lot of rules for them. I have a good portion of them listed here, and the video I have embedded here does a good job of explaining it a bit better than I do because he works with them through example. I'll have this linked in the description as well,
Can
like
see.
this. You can see he goes through a list like this, and it might make more sense like that. So, moving on from regular expressions, let's go back first of all and finish these up here. So, we just finished with, I think we finished with package manager. So, what is version control? Version control, when you're working on code, is basically how it is kept track of. So you have like GitHub version control. You have all your code on GitHub, each commit history in a big tree, and you can go through and see, oh, what on this date did I push? I pushed this. Let me get this. Like you can basically look at each version of your program through version control history, and it's well documented. It's easy to use, and it's very important for big projects, specifically where you're working with teams of people. What is a commitment? A commitment is basically the capturing of one version of that code that is in this commit history tree. So basically, there's a bunch of commits in that commit tree, and that would just be one version of it. And you also have to describe basically your changes or what you put in this commit, and it has to be under 72 characters. What is an example of a distributed system, a distributed control system? GitHub. That is a simple one that I use and basically everyone else uses. When should you write tests for your code? Um, Basically, in test-driven development, you would want to write your tests before you write your code. You want to make unit tests. You want to make a system test when you're actually working on big projects, and you make these tests before you make your code. That way, when you make your code, you're making sure they adhere to your tests. So that is that. It's very important for object-oriented programming. What is a database? Database is just a system that manages data, stores it, allows you to perform analysis on the data. You do this with with languages like SQL, which the next question is, what is SQL? And SQL is a language used to interact with a relational database. What is the most common type of data structures? Arrays, lists, and vectors. What is the difference between a singly linked list and a doubly linked list? First of all, let me explain what a linked list is. So we can go here, linked list. So you can see a linked list is this. Um, you have the data, and then you have the next, and it is basically the next, it points to the next object in this list. It's not a list through a traditional built-in library per se. It's a list that you built yourself. And the way it works is you have the head node right here. This is the head node. You have your data A, and then you have your pointer. Your pointer next points to the next piece of data. So the next piece of data would be B. B has its data B, and its next. Its next goes to C. C has its data C, and its next goes to D. D has its data D, and its next goes to null, the end of the linked list. This is a singly linked list. This is the head node, and it basically can only be traversed this way. A doubly linked list works similar, but there would also be a previous spot where the previous would point back to C, and then C's prev would point to B, and then B's prev would point to A, and A's next would point to B, B's next would point to C, C's next would point to D, D's next would point to null. That's the end of the list. And in a doubly linked list, you can traverse backwards, forward, both ways essentially, to traverse the list. And in a cyclically linked list, the only difference would be that this D's next that was pointing to null points back to A. And then that's it. It's a cyclically linked list that you can traverse after D, go back to A, and basically loop through the list cyclically. That is a linked list and the different types of linked lists. What is the difference between a vector and an array? A vector basically can be resized, whereas an array is set to the size that you set it at, and some parts of that array might be null, some will be full. You can't resize it regardless. What is a variable? A variable is basically it becomes whatever you assign it, right? You can have a variable int a, so that would be a variable of type integer. A variable string y, it would be a variable of type string, and you fill this variable with whatever data you propagate in it. What is a class? A class is a collection of data and the operations that can be performed on it. Excuse me. The operations that can be performed on it. So, for example, you could have a class car where you have like data ID. You would have maybe data speed, and then you would have the operations drive, brake, reverse. That would all be encompassed in a class. By operations, I mean functions. What is inheritance? Inheritance is essentially um, the inheritance of a function from a different class into um, another class that is like a subsidiary of that. So you can see here, I have this written. A 2D shape has a perimeter and area. A circle has a radius, and a square doesn't have a radius. Every square is by definition a rectangle, etc. So every square is a rectangle by definition. So that kind of explains that concept, all right? So you have a car and a truck. They also have brake, drive. Maybe you have an inherited class where you could also use the same functions in both, but without defining them in both. Which that also touches on polymorphism, which I'll get into a little bit later. All right, so number theory. So right here, this is pretty simple, but it's very interesting. I will say this. So number number theory is the study of numbers, and by numbers, I mean integer numbers. So 1, 2, 3, 4, 5, 6, -1, -2, no decimals, no fractions, just numbers. So a big concept in number theory is prime numbers. So basically, I just read that. I didn't read it, but I stated what that essentially says. Um, Elucid theorized, um, I can't say his name, but he theorized that there is an infinite number of prime numbers, and he proved this through proof by contradiction. So At its base, number theory is just asking questions about numbers. So FTA basically stands for a fundamental um, theory of arithmetic. Every integer greater than 1 can be uniquely expressed as a product of prime numbers. So you have 12. 12 splits into 6 and 2, and then 6 splits into 3 and 2. Gets us 2, which is 2 and 3, and we have 3 total prime numbers in this. So that includes, I believe, the prime numbers for that. Number theory is used for encryption schemes. It's used for basically every encryption scheme um, through networks. And the reason for this is because if you take two extremely large prime numbers and multiply them by each other, even a supercomputer would very much struggle to factorize that. And this is an example of a question using the the counting principle in number theory. How many different phone numbers are possible in the US if a 3-digit area code followed by 7 local numbers cannot begin with a 0 or 1? So 10 numbers total. You omit 0 and 1. That gives us 8 options. You have 8 to the 2. And then you have all of the other numbers can exist. You have 10 to the 8. And then that gives us this answer right here. So remember 10 total numbers, we have to omit the 0, 1, we get 8, and then we multiply 8 by itself because that's how many combinations of the first two digits could be, because they can repeat, so it wouldn't be 8 times 7, it'd be 8 times 8, and then we multiply by the rest here. So that's how that works. And then this is like a little diagram here for the understanding of prime numbers and cryptography. So you can see we have this number times this number, and what that gives us is our secret key, and then we multiply our secret, or this is our secret key, sorry, misspoke. So we have our secret key, and our secret key is divisible by this, and we have our message, which is encrypted, and then to get to the bottom of it, we just divide. It's as simple as that, we divide. But we need to know the secret key to divide properly. We can't just like guess or run it through a system. It's not possible because of how large these prime numbers are. A secret key is a large prime number or product of large primes, which is multiplied by the message and converted to create an encrypted message. So the message is multiplied by the product of large primes, and you basically have your secret key, you divide it by that to get to the secret message. It's as simple as that. And only you and that person can have the secret key, which is kind of difficult to set up because once anyone else has the secret key, they can easily decipher any of your messages that were made using this. That's simple enough. I might have made it sound more complicated than it is, but basically prime numbers and number theory is very crucial to cryptography in modern day computer science. That's like the summary of that. So now to the not fun part, other than finite state machines. I'm not going to touch on PDAs. I'm going to leave PDAs and Turing machines to um, these guys right here, which I am going to link. This is
one by one,
I've watched
zero,
this video to study
one,
myself.
one.
Pretty good. It's an MIT video by Michael Sipser, and he's actually the guy who made the textbook on finite automata. So, finite automata is a computer with very small amounts of memory. So, to begin, we have a finite automata right here, and we have our states Q1, Q2, Q3, Q1, Q2, Q3. We have our start state right here. Our accept state is right here. So basically the input for a finite automata is a finite string. The output is either accept or reject. And the way it works is it starts in the start state. It reads from the basically the finite string, starts reading characters and symbols, and it follows the system that is created in the finite automata And if it gets to the accept state at the end, it accepts. It means that the string is accepted in the computer, or it rejects it, and it's that simple. So in this scenario, um, we have Q1, 0 would put us right back in Q1. So if we have a string, if we have a string of, let's say, um, 0011 011, or 0011 010, right? So we have 00 we're still in Q1, 11 0 0 1 0. So this does accept, because in this 0 or 1 put us right back in Q3. So this string would accept. Say, what's one that wouldn't? Anything with 1 1 in this specific scenario gets to the accept state. So 0 1 0 0 0 1. Let's try that. 0, right back to the same. 1 here, 0 here, 0 0, still in Q1, 1 Q2. By the end of the string, we are not in the accept state, we reject. That is how a finite automata works. In simple, it's not overly complicated. Uh, right here, this is some theory for it. Basically, a finite automata is a 5-tuple. The way it works, you have a finite set of states, finite set of alphabet symbols, transition function, a start state, and a set of accept states. And I'm going to leave the theory to him, um, which I will have the video linked if you want to go super in depth about finite automata. Regular expressions. So basically, we already touched on this, but there's also the idea of union and concatenation. I can't speak currently, I'm kind of dehydrated, but um, those concepts exist. You also have the concept of star. So in union, say you have right here, you have A equals good and bad, and B equals boy and girl. These are two sets. A is our first set, good, bad. B is our second set, boy, girl. So if we do the union of sets A and B, then what we get is good, bad, boy, girl. It just creates a new set that has all of them separate. If we do the concatenation of A and B, the two sets, we get good boy, good girl, bad boy, bad girl. So that's how that works. And if we get star, what we get is first we have a null, and then we have a good, bad, good, 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 bad, bad, good, bad, bad, good, 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 bad, and it goes on. So a star is a very long set created from the union of this basic set here. And I wouldn't worry about this as much. Just the concept of union, concatenation, pretty important. But the main idea is the finite automata, basically how they transition, how it gets to the accept, if it accepts or rejects. And that carries on to non-determinism. Basically, in a non-deterministic finite automata, you can be in multiple places at the same time. So I'm going to, that might sound confusing, but I'm going to explain this by example. So basically, the new features of non-determinism are multiple paths, 0 and 1, at many steps. We have this transition, which is a free move without reading input. If you get to Q3, don't need to read input, you can go to Q4 and accept. And then you have accept input if some paths lead to the accept. So I'm going to do this by example. So essentially, let's do an input that will put us in multiple places at the same time. So you see A goes to itself and it goes to Q2. That's non-deterministic already. So if we have a string, we'll say string A, B, yeah, we'll say A, B, A. Let's just try it out. So, or we have example inputs down there. A, B. So A, B, it's A, so it's in itself, or it's A, so it's Q2. So this is in two places at the same time. So the first iteration is in Q1, still in the first iteration. The other version is in Q2. So you're in two places at the same time. Your next one is B. From Q1, you can't use B. It doesn't go anywhere, so you just ignore it. What about the other one? You're in Q2. In Q2, you have B, you go to Q3. That's all you have. You have a null here. You can have a free skip to go to Q4, and you accept. Okay, AB accepts. Even though both versions don't get to the accept state, one of them does, so it does accept. You have AA, A, A, so you're in itself for the first one. A, there's no A. You're stuck in Q2, you can't go to Q4, the accept state, you reject. ABA, A, B, there's no B. You're just stuck there. And then you have ABA, so A, B, or A, B, and then A. So if you have ABA, the first one's here, A, B, A, or here again, you don't accept there. But the other version of this ABA, A, B, A gets to the accept state. So as long as one of them gets to the accept state in a non-deterministic finite automata, you do accept. You don't need both, you just need one. ABB rejects, let's see, A, BB, nothing, A, B, nothing. Or A, B, B, there's no B, it rejects it. I know there's a free square, but there's still the B that it requires right here, and there's nowhere to go with that, so it rejects. So that is kind of a non-deterministic finite automata by example. Hopefully that makes sense. If not, please do more research on this. It is not overly complicated, but it's kind of different to grasp the concept of. Context-free grammars, basically, to generate strings through a context-free grammar, you would write down the variable, replace the variable according to its rules, repeat until only the terminal remains, and the result is the generated string. You can see here you have a tree, a parse tree. You have S, S goes to 0, S1, which S goes to the same thing, 0, S1, or S can go to R, which you can see here. So it finally goes to R, and then R goes to null, and then you get to null. That is how that is created. Not overly important if we're doing this from a very surface level perspective. So don't worry overly about that, but it is an important concept. A context-free grammar is a CFG. It is a for tuple with a finite set of variables, a finite set of terminal symbols, a finite set of rules, and a star variable. This is an example. Similar to the one I just went over, you see you have E here. E goes to E plus T. T goes to either F or TXF. So you get to here, you go to TXF here, or you can go to T. T goes to, what does T go to? T goes to TXF or F. This one goes to F. TXF, T here goes to F. F here goes to E or A, which you go to A, and then bam. That is how that is created in a parse tree. Then push down automata, I'm not going to go over, but it is kind of like a finite state machine that adds a stack to it. I'm going to leave this if you want to learn about it. I'm going to have all these links in the description. This is a PDA, it's a 7 tuple. I'm just going to briefly show this. I'm not going to actually go over it. And then a Turing machine is the final state, final type of automata. And it's basically, a PDA uses a stack and is limited to context-free languages. A Turing machine uses infinite tape and can simulate any computation and recognize recursively enumerable languages. So a Turing machine is the best type, in my opinion, of a finite state machine. Basically, it reads from the tape, it read-write from the input tape, and it can move left or right, and the tape's infinite, and it can reject or accept at any point in time once it reaches whatever requirement you gave it. Say you were looking for the same amount of A's and B's, in a sequence it finds AA, BB, it can just stop right there and be done. I'm not going to go super in depth on this, um, just for time's sake. That's also kind of hand in hand with a PDA, so that's also going to be linked in the description. So, computational complexity theory. This is just time complexity in a fancy wording. The way this works, basically different algorithms. I'm not going to go over this in the context of a finite state machine, but maybe I will. So in a multi-tape Turing machine, you have your input string. You're going through it one by one. The time complexity on that would be simply the length of the tape. So big O n, n being the length of the um, of just basically going through the input tape one iteration. So definition of complexity theory is model dependence, but dependence is low. For reasonable deterministic models, you focus on questions that do not depend on the model choice. I don't think that's a good definition. I think that's something from his lecture, but anyways, time complexity in algorithms is pretty much the same as a time complexity here. Say we have a search algorithm, right? So let's see, linear search algorithm, right? So a linear search algorithm, you have a list of numbers, they're unordered, and you're basically going through it one by one by one, looking for your specific number that you're searching for in that list. So the complexity would be big O n, because basically it's just going through it one by one. And a binary search algorithm, the time complexity, would be big O log n, because a binary search complexity, it goes to the middle, it cuts that in half, it keeps looking, it reduces the search space by half at each step, and the maximum number of iterations required is log base 2 of n, where n is the size of the array. So you have different time complexities for different algorithms, which I have a cheat sheet for. I think it's at the bottom. Yup, right here. So let's skip to this real quick. Ignore that. That's for data structures. So we have right here linear search time complexity. Best case is big O1. So that's if you first try and the linear search found it, but on average it's big O(n). Bubble search is on best case O to the n, and the average case is O to the n squared. Heap sort is on average uh, O n log n, and then insertion is right here. Best case big O n, average case big O n to the squared. Merge search right here. Quick search. I'm not going to go over each of them, but they are there for basically a cheat sheet. And the reason for these being different time complexities is because they are different search algorithms. They have a different process, and this process you can calculate the time complexity to be these. You can memorize these, you can learn how it's calculated, whichever way is best, or just know that they exist, that different algorithms have a different time complexity, because that is a root concept in computer science. So moving forward, let's talk about operating systems, threading, and multi-threading. So this is, first of all, I guess I'll just talk about the cores of your CPU. So you have basically an amount of cores on your processor, and these determine the amount of things that can happen at the same time. If you have an 8-core processor, you can do 8 operations at the same time, because parallelism, each core does its own operations. 4-core, you can do 4, and you have a clock speed as well for your core, which for this example, 2.6 gigahertz is the clock speed. And this is a core, and then this is your overall CPU. And a thread is one program or set of operations that needs to happen. So you could have a bunch of threads in a specific program, which I'm going to explain right here. You can see this is a CPU operating system. Where'd you go? This is Basically, like you go to your task manager, you can see down there, you have 1,877 threads currently running at the time of this picture, like when I took it, which is 175 processes. Each process has numerous threads, and basically your CPU cores handle these processes. Um, that is how it works. So a little bit more complicated, we get here. We have in a single core, we have a thread T1 and a thread T2. So T1 right here and T2 right here. All right. So first, what we're gonna do, T1 is telling us to print 1. So first we print 1, no problem, right? No problem at all. Then we tell time sleep 10, so we sleep it. The way your operating system works is it is basically scheduling these threads um, as efficiently as it can, because you don't want to just time sleep and then your computer can't use that core, it's just sitting there, there's nothing happening. That would not be good. So we have print 1, time sleep 10. So after we sleep 10, we skip to our other thread that we can work on while this is sleeping, right? So print 1, time sleep, we skip to this thread. Okay, let's see what's in this thread, print 2. Okay, we're done with thread 2, let's go back to thread 1, see if it's done. Thread 1's done, we'll print 3. Bam, finished. So we get the output 1, 2, 3. Our core has these threads, T1, T2. We print 1, we sleep, we go to thread 2, we print 2, we go back to thread 1, we finish thread 1. That is the idea of threading. It is to keep the operating system as efficient as possible. You don't have to do anything for this. The operating system handles this on its own. And it's simple enough to understand conceptually. This is an example of this in Python using the threading import and time import. Basically, this function is defined. You print ran, you sleep, you exit, you go do the next thing, you come back, you print done, you sleep, you go to the other thread, finish that, you come back, you print, now done. So you can see the output we get is ran first, then we sleep, so we print 2. And 2 comes from this. It's print threading active count. The amount of active threads is 2. We print that. Okay, we're done with that. We come back here. We print done. We sleep again. We come out. And then what is printed after that finally is printed. And then we go back to our original thread and we finish with now done. That is basically the scheduling order of the threads in this example. That is how threading works. There is also multi-threading, a bit more complicated, which I'm not going to go super in depth on, but for multi-threading, we need synchronization constructs like mutexes, semaphores. I'm not going to touch on that in this video, but the way they work is basically to make sure that only the correct parts of the code are accessed at the correct time to prevent deadlocking, stuff like that. So what else do I need to touch on for the operating system and threading? This example is pretty good. So you see here you have a client, and this is how it used to work a long time ago, thankfully. And this is in a singly threaded system, all right? So in a singly threaded system, this is someone and this is someone. This is like Jim and John. They're trying to access the same website. They ordered a shirt, and John ordered it first. So he has his first order in the queue of requests. He's right here. It goes to the singly threaded system. He enters a request, gets him his stuff, and then his is next up. Okay. That's how a singly threaded system works. A multi-threaded system, John and Jim do it, and it delegates the request to a thread pool, and it handles them basically pretty efficiently. With the multi-threaded system, it handles them relatively at the same time, which is the main difference between single and multi-threading. And then memory space. We didn't really touch on memory space. So a process can have more than one thread, but it needs to have at least one thread of execution. Threads can be scheduled on single CPU architectures and multi-processor, multi-core systems. Threads can be running simultaneously. The idea of parallelism, you can have multiple threads running different times or same times and executing completely different portions of the same process. This is parallelism. The process has its own address space, And threads share the parent process address space and any other threads that the process created. Basically, threads are a extremely lightweight data structure compared to processes, and it helps the operating system handle the massive amount of tasks that are going on in a very efficient manner. So that's how that works. Yeah, there's not that much left. So the remaining stuff is um, kind of the most important, to be honest, because I'm not going to touch on like object-oriented programming very much because that is a massive thing kind of on its own. I do have this short section here on it. Um, Nothing like overly intensive event-driven programming, just kind of what it is. And then data structures and algorithms. This is a massive part of computer science, but nonetheless, I'm going to try to keep it as simple as I can in this video. So, first of all, um, you have here it is. All right,
Say we wrote a function that goes through every number in a list and adds it to a total sum variable.
time
If we consider
complexity.
adding to be one operation, then running this function on a list with 10 numbers costs 10 operations. Running it on a list with 20 numbers costs 20 operations. Say we wrote another function that just returns the first number in a list. Then no matter how large the list is, this function will never cost more than one operation. Clearly, these two algorithms have a different time complexity, or relationship between growth of input size and growth of operations. We communicate these time complexities using big O notation. Referring to input size as n, common complexities are constant, linear, quadratic, logarithmic, n log n, exponential, and factorial.
And that's what I touched on earlier with the time complexity. Um, Basically, you have different time complexity for different algorithms, and O to the 1 would be like the ideal world. You guess the right number instantly, and that's how it works. These other ones are
First
different
algorithm runs in O
algorithms,
of n, meaning its operations
which I'm going to skip over that. Um, for data structures, an array is our first one.
ninth element into an array meant for 8 elements. An array is an indexable contiguous chunk of memory. Arrays are fixed size. You can't insert a ninth element into an array meant for 8 elements. A list data structure with a flexible size is a linked list. The idea is to package your data into nodes that hold 1, your data, and 2, a pointer that points to the next node. Traversing a linked list reminds me of those YouTube direction chains. Like you see a comment that says, read my
So we have binary trees as well.
next node, nodes pointing to a left and a right child node. This is called a binary tree. These child nodes can also be called subtrees since trees are recursive in nature. A node with no children is called a leaf node, while a node with 7 children is my mother-in-law. A common type of tree is the
That joke's a little out of there. And then we have heap trees.
trees. Another type of tree is a heap. The primary difference between this and the binary search tree is I actually use this one. It's also sometimes called a priority queue because at the root of it is always the highest priority element. A min heap will have the min element and a max heap will have the max element at the root. But don't get me wrong, the rest of the heap is unsorted. It is an absolute wasteland down there. Searching is
We have stack trees.
array. One way to traverse a tree is a depth-first search, which is like going deep, fully exploring one path, and then moving on to the next. One way to visit this tree in a depth-first order could be to start at 10, go to 13, go to 4, then 6, then 12, then 8, and then 1. Whereas another option is a breadth-first search, where we view it more level by level. A way to print this same tree in a BFS manner could be 10, 13, 12, 4, 6, 8, 1. When it comes to implementation, depth first search can use a stack. A stack is a list-based data structure where the only two operations are
In a stack, you can only push and pop. Basically, pop is to remove whatever's at the top of the stack. It just gets rid of it. Push would be push to the top. I say top and whatever, same thing. That would be the idea of a stack, which
are
we're
add to
gonna
the
probably
end
show.
and pop from the end. This makes a stack LIFO, last in, first out. DFS are often done using recursion, which indirectly uses a stack, the recursive stack. So if your recursion
And I'm not gonna let that keep playing because it's a bit complicated. That's really it. There's hash maps, there's graphs. Hash maps, basically, I'll let him do a quick little.
hash maps are sort of the holy grail of data structures. With basically constant time retrieval of data, the saying goes that if you don't know what you're doing, just try throwing hash maps at the question. As an example, one time I was in a coding interview and froze, so I just told the interviewer, well, this is called collision. One the same hash code if given the same key.
So you have a key and you have a value, and basically the hash map, you can give, for example, age map, which is like the hash map for this trend black. You would get the value 20, which is matched with it. If I were to give it polymers, I'd get 17. That is the idea of a hash map. It's a pretty simple concept, not overly complicated. But that's kind of the ideas of some of the data structures. There's obviously lists, there's arrays, there is all kinds of other data structures, vectors, um, and for data structures and algorithms, algorithms are simply, there's already a lot of existing ones, like these, for example. Um, you can make your own algorithms as well. It's kind of the idea of data structures and algorithms. The main thing I learned when I was in this class is I did some cool projects that included like hefty amounts of lists of objects is what I mostly worked on, or like a very complex um, like arrays. For example, like one of the projects I worked on, I made like a hemorrhagic smallpox simulation where I had people, I had schools, um, schools. I had different groups, mixing groups, and each of these had their own object class. And in the simulation, I would go through the list of, I think it was like 50,000 people I did in the list, and each person object had their own ID. They had their own just like name and stuff, just randomly generated names. And they also had the ID, like the status of infected or not infected. They also had like the days they were infected, and I would go through the simulation, and it would basically put people in their mixing groups, their family, their work, their school. People were different ages. People had family groups, and it would basically use all of these data structures to see how many people became infected by the end of it. And I would infect a small mixing group, run the simulation for a set of days, and I would traverse these huge different lists that all were separately organized according to what I needed them in, like mixing groups of people at school. So a list of people at their schools for that time iteration, how they interact. If they were at school, then they came in contact with someone who's infected, then they become not infected off the rip, but they have a percent chance based on the paper I based this work on to become infected. That's kind of the idea of data structures and algorithms. You kind of just use it for your programming. The idea of time complexity also is in there. Some of these search algorithms, of course, the data that he just went over, like the data types, arrays, linked lists, binary trees, hash maps. That's kind of the idea of it. I can't really teach data structures and algorithms through like a YouTube video where I'm just kind of lecturing in a way. But this video does a good idea of summarizing it, and I also have that linked. Event-driven programming. So event-driven programming, very simple. So basically an example of this would be in like node.js, a JavaScript file. It allows the application to respond to events like HTTP requests or file I/O by attaching callback functions and event listeners, making it suited for asynchronous operations. So if I have an event listener that listens for a like the mouse to move, and then it pops up with "Hey, what are you doing?" or something like that. That would be an example of event-driven programming. Once an event occurs, mouse moving, event happens because it has an event listener. Could be also just like a button click, clicked on this, oh, pops up. A mouse drag, which I already did an example of. Stuff like that. That is event-driven programming in simple. Object-oriented programming. So this is one where I can't go crazy in depth, but I need to give you everything important about it, which I will. So for object-oriented programming, there are four pillars, and these are the main concepts of it. You have encapsulation, encapsulation, abstraction, inheritance, and polymorphism. So encapsulation is basically an object exists, contains data and functions, and it's the switch from having external variables that are fed to a function to having an object with the functions and data encapsulated. So this is also similar to the dry concept I talked about earlier, right? If you go way up here, if you remember earlier, what is the dry principle? To compartmentalize your code to create functions that perform smaller tasks so your code is optimized. This is the same idea, but inside of an object. So you have an object of a car. The car drives, brakes, reverses, whatever. Basically, those functions are inside of that object. That is encapsulation. So you can see here we have this version, base salary, this. over time, right, they're just defined. The variables are just defined. They're in the open. You have get wage, give it all of these functions, and then you get that. Inside of object, you have these variables defined. You can see all you have to do is take this, and you can simply call getWage function employee.getWage. You don't even have to give them these variables because it's already inside of that object. That is one of the core ideas of object-oriented programming, is very important to it. Abstraction is the process of hiding the implementation details of a class, exposing only the essential features that the user needs to interact with it. So the idea of that can be shown here. You have public and private class functions in a class. So public void make sound. You can call cat make sound. It would do this. You'd also have a um, private data somewhere, which, let's see, do I have an example in here of that? Doesn't look like it. Anyways, basically you have private and public data inside of a class, inside that object. The object is an instance of a class. Basically, you would have the ability to call functions like get ID to get the private data ID of that object. Um, that is the idea of abstraction. It also, in simple, it basically just hides complicated um, functions and stuff from like the user. So start, stop, accelerate, brake would all be working inside of the object, kind of like I explained for the last example. Okay. Polymorphism. So polymorphism essentially means that you have multiple methods with the same name, but different parameters. So you have a same name with no variable inside, no string n, and you have same name with string. You can basically override the same name by putting the string inside, and you can just call the basic say name by just doing say name. It's the same function, but um, it can be overridden. Basically, I don't think I'm explaining that very well. Let me just read it. Polymorphism means you can have multiple methods with the same name but different parameters. An example would be the function say name and say name string in this class, in the same class, and be called the same name but different parameters. Overriding a method is another aspect, and an inherited function can be overridden, and you create the same name function with the same parameters. It will override the inherited function. That's what I was trying to explain just off the dome. Was not explaining it very well. And then, did it not touch on encapsulation, abstraction, inheritance? Yeah, inheritance. For example, say I have a class dog, right? And in class dog, this is pseudocode. I'm not going to actually do much. I have the function bark, um, bark, whatever, right? Pseudocode. So um, all I have to do, there's also like the class dog at the top. So this is Java. Pretend this is Java, right? All I have to do, I have my new file. I include dog.h, whatever it is, and then what I do from there is I should be able to have what is something else that barks? A wolf. A wolf is somewhat a type of dog, we could maybe argue, right? So wolf has this included. Wolf can do bark, even though wolf's functions do not contain bark, right? Class wolf, and wolf can run, right? So I included dog h, pretend wolf's a subsidiary of dog, and wolf can bark, but dog cannot run, even though dog should be able to run. It's a bit backwards, but for the example, hopefully that makes sense. That's the idea of inheritance. And lastly, I'm going to talk about database systems and modeling. So, in simple, a database is an organized collection of data. A DBMS is a database management system, which is software to create, manage, and query databases. SQL, MySQL is a good one. I use MySQL Workbench for the stuff I do on the back end. A schema is a structure of the database, tables, fields, relationships, all of that. SQL stands for Structured Query Language, and a relational model is data stored in tables, unique tuples, and attributes, which is just rows and columns. Tuples are rows, attributes are columns. And then it also uses primary keys, which every table should have a primary key. So the primary key is like an ID, something unique to each single table, like not table, but each row in the table. And a foreign key links the tables together. So a foreign key would be linked in the second table, linked to the primary key, and that's how you can set up a relational database table where one table is connected to the other. And you also have the idea of cardinality. So you have database relationships like one to one, which is like an entity in A is related to B to one in B. So like, let me think of an example. Students in a classroom. So you have the database students. Each student has their ID. They have their courses enrolled, and say, no, I have an idea. Course. You have the table course, and then you have the table professor, right? Each course is taught by one professor, and each professor is teaching one course. Pretend that's a requirement for some reason. That's they're teaching one course. So that professor would be in a one-to-one relationship there. One to many, you have a course. The course has many students, so one course to many students. Many to many um, would be, I can't think of an example off the top of my head. I'm sure there's easy ones, but you get the idea, the fundamental idea of that. That is the idea of cardinality and database definition, database management definition. It's kind of hard to show, but I will go to um, so right here we have the database patients. So we run this, select star, which is, if you remember, it's not the same here, but from regular expressions, that would be the optional one or many of that same character is what that would be in regular expressions. That's just like a little pop quiz. So select star from patients, and this is just getting us basically all of the patients. We have patient ID. This is the unique ID, the primary ID, and then we have the first name, last name, gender. This overlaps, whatever. Allergies, height, and weight. So you can see these are all different. That's why it's a unique ID. You need them to be different. If we were to do, let's say, select from, I think there's another table, right? Don't remember. Fourth line at the products, right? You see it's the same thing. It's the same idea. I'm not going to go much more in depth for SQL. There's ways to create your own table. You would do create table and then the name and then other. There's ways to insert. One of the things I recently did, um, what we did, my project, is I took a bunch of weather data from each state, was able to find like the average temperature, stuff like that. And you can use SQL and MySQL Workbench to do so. And that's all I have in my document, which keep in mind I used this document to review for my exit exam. There's stuff that I already felt comfortable with. That was just so basic. I didn't feel like keeping it in here. Stuff that I didn't want to have in this document for future purpose because it is overly complicated. This is kind of like a easy to middle of the pack definition type document with basic examples of some of the overarching concepts of computer science, which I think would be useful to someone who's going into the field. They learn this stuff, the basic idea of it, the concepts of it, then they dive in. So it's like a kind of little introduction to it. You dive in, learn it in depth. I think that's the best way to learn. So you understand it conceptually and then can connect the dots later on. So hopefully this is useful to anyone who actually watches it to the end, if anyone at all. If anything, it's going to be good for me to come back to study if I ever need to, although it is pretty basic. Who knows? Maybe I just lose my whole memory or something in the future. Who knows? But regardless, thank you for watching. My name is Cody Raby. I am a soon to be graduating computer computer science student, and that's kind of like the basic idea of computer science. Some of the fundamental concepts I was taught in it that aren't as on the nose as just like programming, hello world, stuff like that. Regular expressions, um, some of these definitions and stuff. Of course, variables, classes, structs, which I don't think I went over structs, but it's pretty similar to a class. SQL, database management, uh, finite automata, text editors, operating systems, threading, multi-threading. There was also word matching with regular expressions. Yep. Number theory, that was big too. Prime numbers for encryption. Huge prime numbers are used for encryption, which if quantum computers ever do come along, we are going to be screwed. But for now, they don't exist. Counting principle, automata, Turing machine. I didn't go over PDAs. A stack is another type of data structure I don't think I went over, but it is just kind of like a queue at the top, whatever the most recent one comes off or gets added to it. You go from the top, and then I went over time complexity a little bit, linear search algorithm, big O to the n. Um, Binary search algorithm would be log n, um, log 2n. And then you have threading, the idea of threading of cores. You have parallelism. You have the switching of the cores of the threads that are being ran. Data structures and algorithms, I went over the time complexity cases. I went over the types of data structures. Event-driven programming, which is basically like listening for a mouse click or stuff like that. Object-oriented programming, encapsulation, trying to keep stuff inside of the object where it should be. Abstraction, similar to that. Basically, the process of hiding details that the user might not need to know about, like how break works. You're simply calling break, you're simply calling drive. You don't need to see all the code for how that works. Inheritance, I already went over. Inheriting from another class that is a top class, like a rectangle and square. Think a rectangle and square. They're the same, but they're different, so they have same functions that can be used by both if inherited. Polymorphism, that is the idea of basically overriding methods. You have the same function, you can override it. Um, that's the idea of polymorphism. Databases modeling, cardinality, use SQL, a database management system. That's all I got. I mean, this doesn't touch on every little nuance. That would be absurd. Computer science is too big of a field. There's a lot I didn't go over. I didn't go over binary. I didn't go over some of the basics, but hopefully this is like a good I wouldn't say a jump in the deep end. So you got a swimming pool and you start off shallow. It's about here. You start off shallow over here, okay? Gets a little bit deeper, a little bit deeper, a little bit deeper, and it's like bam, it's gone. It's deepened. We're not jumping into shallow end. We're jumping in about right here, and it gets deep, and then it shanks off. We're jumping in 2 feet past the shallow end. So that's what this video basically is going over. Pretty basic. Some concepts a bit harder, some easier, but um, nevertheless, that's all I got. Hopefully it was useful. Take it easy. Have a good one.